Okay, so now let's go ahead and see what would be the operation of a fully controlled thyristor rectifier, which essentially implies that we would replace all the 4 diodes of the diode rectifier with the 4 thyristors. So this is how the circuit of a fully controlled diode thyristor rectifier looks like, right? For simplicity, let us start with the assumption that we have an highly inductive load, and these 4 are thyristors, so let's call them T1, T2, T3 and T4, right? And this is your AC voltage, which is connected to the midpoint of the 2 thyristor legs, right? So this is plus Vin, right? So let us try to analyze the operation. Let's name this as output current, and this is output voltage, and this is input current. This is the input voltage Vin, right? And let's say this is the angle alpha, where now earlier, because we had only 2 thyristors, so we were triggering one in one half cycle and another one in the other half cycle. But now here, because we need a closed path for the current to flow, so we triggered 2 thyristors, T1 and T2, in the first half cycle at alpha, and the remaining 2 thyristors at pi plus alpha, which is T3 and T4, right? So let me now just extend these points for the other current waveform. So now let us draw the current I in, right, and the output voltage VO in the same graph. So if we start again, as we discussed before, it's better to start at an instant where you are triggering some devices. So let's start at instant alpha and let's start drawing the waveform from their point. So what happens at alpha? At theta equal to alpha, if you see, you need to first check whether T1 would conduct or T3 would conduct, and similarly whether T1 and T3, yeah, one of the top 2, and whether T2 or T4, one of the bottom 2. So you can see that at alpha, the anode of T1 is at a higher potential as respect to anode of T3, right? Moreover, you are giving trigger pulse to T1 anyways, so yes, T1 would conduct and T3 will not conduct. Similarly, you can compare between T2 and T4, and what you would realize is that T2 will conduct and not T4. So at theta equal to alpha, and subsequently T1 and T2 conducts, so you can write T1 and T2, right? Sorry, let me just write T1 and T2, and you can see that if these 2 will conduct, the output voltage will be equal to the input voltage, and the current input will be equal to the output current, which, if we are assuming highly inductive load, that is, we can consider it to be almost constant DC, right? So far so good. It's very similar to half control. Nothing much has changed till now. Let us see what happens subsequently. So at theta equal to pi plus, what happens? Again, let us think in terms of the devices, which one would conduct. Okay, now T1 was already conducting, right? T3 we have not given trigger pulse, we'll give it at pi plus alpha. So at pi we have not given any trigger pulse to T3. So T1 would continue to conduct irrespective of the anode potential. Similarly, among the bottom two, since T2 was already conducting and we have not given a trigger pulse to T4, so T2 will continue to conduct. So here T1 and T2 will continue to conduct. If T1 and T2 are conducting, then the current would flow in this way, right? And the output voltage would be equal to the input voltage, and the input current will be equal to the output current. So what happens is, in this period also T1, T2 conducts, the current remains the same, right? So current does not come back to zero, remains the same, and the output voltage continues to follow the input voltage. Now the input voltage is going negative, so the output voltage also goes negative in this case. So this, you see, is certainly a difference between the half controlled and the fully controlled, right? HC versus FC. Now what happens subsequently at theta equal to pi plus alpha. At theta equal to pi plus alpha, you can see that we can again compare among the devices and see which one would conduct, right? So now if you see at just before pi plus alpha, T1 was conducting. At pi plus alpha we have given pulse to T3. So now potentially both of them can conduct depending on, or either of them can conduct depending on their anode potential. So which one will have a higher anode potential in this case? You see input voltage has already become negative, and therefore the anode potential, therefore the anode potential would be higher for T3 rather than T1. Why? Because the input has reversed. So therefore T3 would be the one conducting instead of T1. Between T2 and T4, again, although T2 was previously conducting, but you have given a trigger pulse to T4 also, now potentially either of them can conduct. And now if you check the voltages, you realize that T4 is the one which is at a lower cathode potential, so T4 will conduct. So in this next phase, T3 and T4 conducts. If T3 and T4 conducts, then the input current is negative of the output current, and the output voltage is the negative of the input voltage. Now you can analyze what happens at theta equal to 2 pi, right? At theta equal to 2 pi plus, again you can analyze, and you would realize that by doing the same analysis that T3 and T4 will continue to conduct, and therefore in this initial period also T3 and T4 conducts, and the current is negative, right? And the voltage is also negative. So this is how the output voltage waveform looks like, and this is the corresponding input current. Now let's see what happens in terms of the output average voltage, right? Or let's just look at the power factor first and then move on to the average voltage. So what is the power factor here? You see, power factor is, so power factor in this case again would have two components, the distortion power factor, which you can calculate, it's a square wave current, right? And a displacement power factor. Now again, if you see this waveform and if you try to draw the fundamental current of this square wave, then this is how approximately you would draw it, right? And which sort of indicates that the zero crossing would be at alpha, and therefore here power factor would not be alpha by 2 but would be alpha. So power factor might be a little bit poor than what was in the previous case. Okay, now once we have found the power factor, let's move on to find the average output voltage. Now here the output voltage obviously looks a little bit different. You can still write the expression for average output voltage, which is 1 upon pi integral 0 to pi Vm sine theta d theta, right? You can split this integral into two, 1 upon pi integral 0 to alpha, right? Vm, sorry, this is not this thing. This is VO, instantaneous value. So you understand that VO would be equal to minus V in, right? VO would be equal to minus V in during the period 0 to alpha. So you can write this as minus VM minus VM sine minus, let's first write in terms of Vn. So we can write it as minus V in d theta, right, plus 1 upon pi integral alpha 2 pi V in d theta, right? You can break it into two phases, and now this expression you can further rewrite it as 1 upon pi integral 0 to alpha minus Vm sine theta d theta plus 1 upon pi integral alpha to pi Vm sine theta d theta, right? And now you can go ahead and you can integrate it, and what you would get is 2Vm by pi cos of alpha. This is your output voltage expression, right? So one thing now you would observe here is that as you change the value of alpha, right, going from 0 to pi by 2, right, this value, so as we go from 0 to pi by 2, we see that V0 voltage, average value of V0 would actually go from a positive value, right, it will go towards a 0 value, the max value to 0 value. And in terms of alpha, if we go from pi by 2 further towards pi, then we see that this value will go to the negative max value. And what does that imply? That implies that this converter can give you output voltage, average voltage, both positive as well as negative value, right? And that is what is makes it unique, makes it different from the half controlled rectifiers. Okay, now this is one of the things. So because of that, we can see that if we draw the average current and the average voltage, it can certainly, the current will be only positive, right? Current cannot be negative. Why? Because if you see the circuit, if you physically see the circuit, you realize that the output current cannot flow reverse because there are thyristors and they cannot allow reverse current direction, right? So therefore the output current will always going to be positive. The output voltage can be positive if alpha is between 0 and pi by 2, and output voltage can be negative if alpha is greater than pi by 2. So it can operate in these two quadrants. You can see that in the quadrant where both current and voltages are positive, so the real power is flowing from the AC side to the DC side, right? And in the case where the current, so in the case where both are positive, the power is flowing from AC side to DC side, right? And if in the case where the average voltage is negative, output power is V into I, so it becomes negative. So the power actually flows from DC side to AC side, right? So this is the main difference between the two quadrants, and this allows much more flexibility. This allows for more applications wherein this circuit could be used. Okay, now that said, how do you actually make power flow in the reverse direction? For example, let's say if you have a DC, if you have a battery, right? So now this is your circuit, right? Instead of drawing the full circuit, let me draw just this symbol which represents it's a full bridge kind of configuration made up of thyristors. And now in the output you have, let's say, a large inductance, right, which ensures current is continuous, and you have a battery here, right? And now you can regulate. So this voltage is V0. V0 is given by 2Vm by pi cos alpha, right? There is some resistance. So you can adjust this voltage V0 such that this current flows from left to right and your AC side is charging the battery, right? Is your I0. So you set your average voltage of V0 little bit higher than this battery voltage E, such that this becomes your average output current, right? If you want to push power back, current will not change, right? If current would have changed, that is could have worked. Since current will not change, so you have to flip the terminal of the battery. So the same circuit, right? You might need to disconnect the battery and connect the battery in opposite direction, right? And now your voltage V0 can be negative, right? So V0 can be negative. So if you see, this is the reference direction. In actual direction, V0 plus here, minus here. This is also plus minus. You adjust V0 such that the current flows in this direction, right? And thereby you are actually extracting power from this battery and you are feeding power back to the AC side. Your power is flowing in the reverse direction. So that is how you cannot change the output current here, right? So you might still have to do some adjustments for power to flow back, but this bridge rectifier inherently, you see, it's not only a rectifier now, you can in fact call it an inverter as well, right? So this full bridge thyristor rectifier, you can call it as a rectifier, you can just call it as a converter, wherein it means that it could either be a rectifier or it could either be operating as an inverter depending on the value of alpha that you choose, whether between 0 to pi or pi by 2 to 0 to pi by 2 or pi by 2 to pi, right? So it could act as a rectifier, it could very well act as an inverter depending on the value of alpha. So it's certainly it can act as an inverter in this range, but it does not mean that whenever alpha is between these two values, it will act as an inverter. I'll give you an example, right? It can act as we have seen above, but let's say if you do not have an active load, you have just an RL kind of load, right? Now, what do you mean by this thing? This means that the load will always consume power. It can never give power back. So now in this case, irrespective of the alpha you choose, you would always be operating as a rectifier, irrespective of the alpha. So what I have written here is only true for continuous conduction mode, right? If the current is continuous, then yes, this is true, because if the output voltage term inverter polarity changes, then the current still is in the same direction and this would mean the power would flow back, right? But if you, let's say for example an RL load, that is not necessary. I'll show you how. Let's talk about the second phase, right? So in this case, in terms of an RL load, let me draw the same circuit. This is R, this is L, right? And this is your output voltage, and now your output voltage value, average value, is actually a negative value, right? If I write the equation and if I say this is average IO, right, I can write as average input voltage is equal to average minus of average output current divided by R, right? Because my IO is VO by R. Since VO value is negative, since VO value is negative, right, therefore the IO value would also come out to be negative, but the average current can never be negative. And therefore, you know, the assumption that in this case what we thought was that the current is going to be continuous and the power is going to flow back in an RL case is no longer true, right? So only in case of continuous conduction mode, if you are able to maintain CCM, then these are true. If you are not able to maintain CCM, for example, as you see in case of just a resistant inductance load, then irrespective of the value of alpha that you choose, you would end up dissipating power, and you might not be operating in continuous conduction mode if alpha becomes greater than pi by 2 in this case, right? So therefore, instead of generalizing this thing, my suggestion would be to see what is the load, to understand the load behavior, to understand the circuit behavior, and then to determine whether the power is actually flowing in which direction depending on the average current and the average voltage values. Yeah. So now next thing that we are going to see is an example of this kind of fully controlled rectifier, where one of the rectifier works as an inverter, other one works as a rectifier. So I would not go into much details about that example, but let me just very quickly show you that example. So as you understand that the HVDC system, right, it is actually a system where you have back-to-back rectifiers and inverter connected. Usually it is a three-phase system, but just for simplicity here, let us assume that it is a single-phase system. So in that case, what will happen? This is your one thyristor bridge, right? Here you have some inductance to ensure current being continuous and smooth, and here you have your another bridge which is connected in the direction such that the current finds a path to flow through it, right? These are again 4 thyristors on one side. This is your voltage, which is Vm 2Vm by pi sine alpha, right, where alpha is the triggering angle for this device. Here you would have voltage 2Vm by pi sine of alpha 2. Let's say this is alpha 1, this is alpha 2, where alpha 2 is the triggering angle for this one, right? Now this is high voltage, kind of a high voltage DC link, where you have one bridge, two bridges connected far apart, and there is a line interconnecting these two bridges. Now what if you want to flow power from one bridge to the other bridge? Let's say in this direction. You want to flow power in this direction, current is flowing in this direction, right? You set the value of both the voltage sources just slightly different. Why? Because if you set it significantly different, then the current would become very large. For example, if you set alpha 1 and alpha 2 both less than pi by 2, let's say, then source 1 is giving power, source 2 is also giving power. So where is power going? Power is getting dissipated in the line. So you cannot do that, right? You have to ensure that roughly alpha 1 plus alpha 2 is approximately equal to pi. It will not be exactly equal to pi, approximately equal to pi. How would it help? If you set alpha 1, let's say for example, equal to 30 degrees, then you have a voltage, positive voltage here, 2Vm by pi sine of 30, and alpha 2 you are setting it to 180 minus 30. That means you have polarity will change, and here also you will have almost the same voltage with the reverse polarity, right? And therefore polarity of both the voltage sources would be polarity will be same and magnitude almost equal. Now you just slightly tune the alphas, slightly tune their alphas from these initial values, and you can control the flow of this current. And depending on the magnitude of current, the current multiplied by the voltage output will be absorbed by this thing. So this would act as an inverter, and the previous one would act as a rectifier. If you want to invert their roles, make alpha 1 equal to 180 minus 30 and make alpha 2 equal to 30. So the current direction would still remain the same, the voltage polarities would change, and the power would start flowing from one side to the other side. So this kind of arrangement, it's also called as a dual bridge or dual SCR bridge configuration, right, which is very popular in not just in HVDC. HVDC is certainly one case where, but in HVDC use a three-phase inverters or three-phase rectifier circuit. Here I've shown you a single-phase circuit where you have two legs. Three-phase would be similar. You will have three legs instead of having two legs. So not just in this thing, but you also see if you, for example, want to operate or interconnect any two AC systems, right, which you may want to operate at either at different frequency, or you might want to operate at different voltages and so on. So you can use this kind of converter rectifier back-to-back connection, right? One is an inverter, one is a rectifier. So with this, we sort of conclude the ideal operation of the single phase thyristor rectifier circuits, right?